The sun rises over what will one day be Montana, casting golden light across a landscape that belongs to giants. The date is impossible to write on any human calendar. It is 66 million years before the first human will walk the earth, before the first primate will climb a tree, before the first mammal larger than a badger will exist. This is the late Cretaceous period, and this is the age of dinosaurs. They have ruled this planet for 165 million years, longer than any empire in human history, longer than most species will ever exist. They have survived ice ages and volcanic eruptions, asteroid impacts and climate shifts, mass extinctions that killed their competitors and left them dominant. They are the most successful large animals Earth has ever produced, and in exactly 10 hours, 75% of them will be dead. But right now, as dawn breaks over Hell Creek, they have no idea this is their last morning. A Tyrannosaurus rex stands on a ridge overlooking a river valley, her massive head silhouetted against the rising sun. She is 40 years old, ancient by Tyrannosaur standards, a matriarch who has survived countless hunts and raised multiple generations of offspring. Her vision is exceptional, better than an eagle's, and she scans the landscape for movement. Below, a herd of Triceratops browses on ferns and low vegetation, their enormous frills catching the morning light. There are perhaps 20 individuals, from massive bulls weighing 8 tons to juveniles still protected by their mothers. This scene has played out millions of times before. The predator watches, calculating odds and opportunities. The prey animals remain vigilant, horns ready, knowing that safety lies in numbers and awareness. Neither predator nor prey realizes that in a few hours, none of this will matter. The ancient calculus of hunter and hunted, refined over millions of years, is about to become instantly obsolete. Further east, along what will become the Gulf Coast of North America, hadrosaurs nest in vast colonies on coastal plains. These duck-billed dinosaurs have created a nursery containing thousands of nests, each carefully constructed from vegetation and earth, each containing dozens of eggs. Some nests have already hatched, and the air fills with the calls of juveniles demanding food from attentive parents. Adult hadrosaurs take turns guarding the colony, while others venture to feeding grounds. A social behavior as complex as anything seen in modern animals. Pterosaurs circle overhead, massive flying reptiles with wingspans exceeding 10 meters, searching the shallows for fish. In the warm waters offshore, Mosasaurs patrol, enormous marine lizards that have become the apex predators of late Cretaceous seas. This world is full, rich, diverse beyond imagining. Over 1,000 dinosaur species exist across the globe, millions of individuals, billions if we count smaller species, an ecosystem that has flourished for longer than the entire age of mammals that will follow. The climate they inhabit is warmer than anything modern humans have experienced. There are no polar ice caps. Sea levels are 170 meters higher than today. Antarctica is covered in forests, not ice. Arctic regions host temperate climates, where dinosaurs thrive in environments that will one day be frozen wasteland. The atmosphere contains more carbon dioxide, making the world a hothouse compared to our current age. But for dinosaurs, this is normal. This is the only world they have ever known. The warmth supports incredible plant growth, which supports incredible animal diversity. Flowering plants, angiosperms, have recently evolved and are spreading rapidly, creating new food sources and new ecological niches. Dinosaurs are adapting to these changes, as they have adapted to every change for 165 million years. Evolution has made them flexible, diverse, successful. But evolution works slowly, across generations, across millennia. And what is coming cannot be adapted to, cannot be survived through evolutionary innovation, cannot be overcome by any amount of strength or intelligence. Beneath their feet, unnoticed and mostly irrelevant to the dinosaurs, small mammals scurry through undergrowth. These creatures are our ancestors, though calling them ancestors seems generous given how different they are from us. They are small, rarely larger than rats, nocturnal, living in the shadows of the dinosaur world. They eat insects, seeds, perhaps small vertebrates when opportunity arises. They are not the dominant species, not the successful species, not the inheritors of Earth. They are survivors, specialists in being overlooked, in hiding, in exploiting niches the large animals ignore. They have survived in this role for over 100 million years, never challenging dinosaur dominance, never evolving beyond modest size or complexity. Why would they? The dinosaurs own the world, and the ecological niches for large animals are filled completely. There is no evolutionary pressure driving mammals to grow large or complex. But in 10 hours, that will change. In 10 hours, being small and hidden and able to burrow will become the most valuable traits any animal possesses. On the other side of the planet, in what will become India, something ominous has been building for millennia. The Deccan Traps, massive volcanic systems, have been erupting for tens of thousands of years, pouring lava across thousands of square kilometers, releasing enormous quantities of carbon dioxide and sulfur into the atmosphere. Some scientists will later argue these eruptions have already stressed global ecosystems, that dinosaurs are in decline before the asteroid hits. The evidence is ambiguous. Certainly, some species show population stress in the million years before impact. But overall, dinosaur diversity remains high. They are adapting to the volcanic disruption as they have adapted to everything else. The Deccan Traps are not killing the dinosaurs. They are merely weakening the resilience of global ecosystems, reducing the buffer that might have allowed survival of what comes next. But what comes next is so catastrophic that no amount of buffer would matter. Even if dinosaurs were at peak health, peak population, peak diversity, they would still die. Because what is about to happen is not a challenge to adapt to. It is simply annihilation. At this moment, thousands of kilometers away in the shallow seas off the Yucatan Peninsula, something is approaching. It has been traveling through space for millions of years, a remnant from the formation of the solar system, a mountain of rock and metal, perhaps 10 to 15 kilometers in diameter. It is moving at 20 kilometers per second, 45,000 miles per hour, faster than anything on Earth moves, carrying kinetic energy equivalent to 10 billion nuclear weapons. Its trajectory was set millions of years ago by gravitational interactions with planets and other asteroids. It has no awareness, no malice, no purpose. It is simply matter obeying physics, and its path will intersect with Earth's orbit in exactly 10 hours, at exactly the worst possible location, a shallow sea containing massive sulfur deposits in its bedrock. If it struck deep ocean, the devastation would be somewhat less. If it struck continental crust away from sulfur deposits, recovery might be faster. But chance, pure random chance, has aimed this mountain of destruction at the one location that will maximize global catastrophe. The dinosaurs, looking up at the stars they cannot understand, have no idea that their doom is already locked in, already unavoidable, already approaching at unimaginable speed. But none of this is visible to the Tyrannosaurus on her ridge. She has decided the Triceratops herd is too alert, too cohesive, and the risk of injury from those massive horns is too high. She will hunt elsewhere, perhaps finding a younger animal separated from its herd, or scavenging a carcass if opportunity presents. She moves down from the ridge with surprising grace for an animal weighing 8 tons, her massive legs carrying her through forest that seems almost designed for creatures her size. And in a sense, it is. The trees, the spacing, the understory vegetation, all of it has been shaped by millions of years of large animals moving through this landscape. The dinosaurs have made this world. They are not just inhabitants, but architects of their environment. Every aspect of this ecosystem, from the largest trees to the smallest insects, exists in relationship to dinosaur presence. They are the keystone species of the entire planet. Remove them, and everything collapses. But that thought is impossible for them to conceive. They are immortal in the way all successful species are immortal. Unable to imagine a world without themselves, unable to conceive that their rule could end. In 10 hours, they will learn otherwise. In 10 hours, the age of dinosaurs will end not with a gradual decline, not with slow extinction over millennia, but with fire and darkness and violence beyond description. This is their last morning. And it is beautiful. 10 hours pass. The sun climbs toward its zenith. Across the globe, dinosaurs continue their routines, hunting and feeding and nesting, oblivious to what approaches from above. And then, in an instant that will echo through geological time, everything changes. At precisely the moment when the sun reaches its highest point over the Yucatan Peninsula, the sky tears open. The asteroid, traveling at 20 kilometers per second, slams into Earth's atmosphere with such violence that the air itself becomes a weapon. The compression wave ahead of the incoming mountain of rock heats the atmosphere to over 10,000 degrees Celsius in seconds. The sky doesn't gradually brighten. It explodes into blinding white light, brighter than 1,000 suns, visible across half the planet. Animals looking up are instantly blinded. The sonic boom that follows is beyond anything nature has produced before, a sound so loud it ruptures eardrums thousands of kilometers away, a physical force that knocks flying creatures from the sky and causes ground-dwelling animals to stumble and fall. The asteroid takes less than 3 seconds to traverse the atmosphere. There is no time for anything to react, no time for the planet to prepare. At the impact site, in shallow seas off what will one day be Mexico, marine life has perhaps 1 second of awareness that something is wrong. The water above them turns to plasma. The light is impossible. Then the asteroid strikes, and everything within 500 kilometers simply ceases to exist. The impact doesn't kill these creatures. It erases them. The asteroid punches through 600 meters of ocean, through the seafloor, deep into Earth's crust, creating a cavity 30 kilometers deep and 100 kilometers wide in the first few seconds. The temperature at the impact point exceeds the surface of the sun. Rock vaporizes. Water vaporizes. The asteroid itself vaporizes, its entire mass of trillions of tons converted to superheated plasma and gas. The ocean doesn't boil away. It is simply annihilated, transformed from liquid to vapor to dissociated atoms in microseconds. The energy release is incomprehensible. 10 billion times the power of the atomic bomb dropped on Hiroshima. All of that energy unleashed in a space smaller than a large city. The ground doesn't shake. It liquefies. Solid rock behaves like water, flowing and surging in waves hundreds of meters high. The shockwave expands outward at supersonic speed, a wall of pressure and heat that obliterates everything in its path. At 100 kilometers from impact, dinosaurs are killed instantly by the pressure wave before they even hear the sound. Their bodies are crushed, bones shattered, soft tissues pulverized. At 500 kilometers, the shockwave arrives as an earthquake of magnitude 10 or higher, something that has no precedent in Earth's history. Trees are ripped from the ground, roots and all. Boulders the size of houses are thrown through the air like pebbles. The landscape is scoured clean, reduced to bedrock in seconds. Any dinosaur still alive at this distance is buried under megatons of debris, or thrown with such force that impact with the ground is fatal. The Tyrannosaurus matriarch we met this morning is approximately 3,000 kilometers from the impact site. She has no warning. One moment, she is tracking the scent of a potential prey animal through dense forest. The next moment, the sky turns white. The light is so intense that even with her eyes closed, she can see the bones in her own skull. Heat washes over her like standing too close to a fire, but magnified 1,000 times. Her skin begins to smoke. Then the sound arrives. A roar so loud it seems to come from inside her own head, vibrating every bone in her massive body. She staggers, confused, trying to understand what is happening. Before she can process the noise, the ground beneath her begins to move. Not the gentle swaying of normal earthquakes, which she has felt before, but violent lurching that throws her 8-ton body sideways. Trees around her, giants that have stood for hundreds of years, snap like twigs and fall in every direction. She tries to run but cannot find footing on ground that rolls like ocean waves. She falls, her massive body crashing into the forest floor. And for the first time in her adult life, she experiences something she has rarely felt: terror. Thousands of kilometers away in other directions, other dinosaurs experience their own versions of apocalypse. In what will become India, a herd of Titanosaurs, the largest animals ever to walk on land, animals weighing over 70 tons with necks stretching 20 meters into the air, see the horizon flash white. They are so far from the impact that the light arrives before the pressure wave, before the sound, giving them precious seconds to witness something their brains cannot interpret. Some of them turn toward the light, curious or confused. Then the thermal pulse arrives, carried by the initial flash of impact, and the air temperature spikes by hundreds of degrees. Their skin, designed to radiate heat in the tropical climate they inhabit, becomes a liability as ambient temperature exceeds body temperature. They begin to overheat catastrophically. Smaller dinosaurs nearby, with higher surface area to volume ratios, fare even worse. Some simply collapse, their nervous systems overwhelmed by heat they cannot escape. In the shallow seas of the Western Interior Seaway, which currently splits North America into eastern and western land masses, marine reptiles sense the pressure wave through the water before it reaches the surface. Mosasaurs and Plesiosaurs, predators that have ruled these waters for millions of years, feel the disturbance and dive instinctively, seeking the safety of depth. But there is no safety. The seabed itself is convulsing, fracturing, releasing gas and sediment in massive plumes. Then the surface pressure wave hits, and the water itself becomes a weapon. Tsunamis form instantly, not the gradual building waves of normal earthquakes, but walls of water that appear fully formed, racing outward from the epicenter at hundreds of kilometers per hour. Marine reptiles are caught in these massive waves and thrown hundreds of kilometers inland, far beyond any shoreline, their bodies eventually fossilizing in landlocked sediments that will baffle paleontologists until they understand the scale of what happened here. Meanwhile, at the impact site, something even more catastrophic is unfolding. The asteroid's kinetic energy has excavated a crater, but Earth's crust is not simply passive. The impact has compressed the crust so violently that it rebounds, like a droplet of water splashing in reverse. Rock that was driven 30 kilometers deep surges back upward, creating a temporary mountain taller than Everest, a peak of molten stone rising in the center of the impact crater. This peak forms and collapses within minutes, its debris spreading outward to create the characteristic ring structure of large impact craters. But more dangerous than the collapsing central peak is what is being launched into space. Millions of tons of rock, vaporized and molten and solid, are thrown upward on ballistic trajectories. Some of this material reaches escape velocity and leaves Earth forever, fragments of our planet hurled into space by the impact. But most of it follows parabolic arcs that will bring it back down across the entire planet. This ejecta curtain is perhaps the most deadly aspect of the impact for dinosaurs far from ground zero. The material launched into the upper atmosphere and space begins falling back within minutes, and as it re-enters Earth's atmosphere at orbital velocities, friction heats it to incandescence. Imagine a meteor shower, but instead of a few streaks of light, the entire sky fills with millions of burning fragments, some as small as sand grains, others as large as houses. These fragments rain down globally, and each one adds its kinetic energy to the atmosphere as heat. The air temperature begins to rise. In some regions, it rises to 200 degrees Celsius or higher. Anything caught in the open begins to cook. Feathers smolder and ignite. Skin blisters. Small dinosaurs, those under a few hundred kilograms, have nowhere to hide from this thermal assault. Their body mass is too small to buffer against the temperature spike. They overheat within minutes, their brains literally cooking inside their skulls, causing seizures and death. Larger dinosaurs last longer, their mass providing thermal inertia, but even they cannot escape indefinitely. The lucky ones, if luck has any meaning in this catastrophe, are those near water or in caves. Dinosaurs caught in rivers or lakes dive beneath the surface, where water absorbs the thermal pulse and provides temporary refuge. Those in deep caves or heavy forest canopy are shielded from the worst of the radiant heat. But these are tiny minorities. Most dinosaurs are caught in the open, in clearings or plains or coasts, with no shelter available and no understanding of what they should do. They run because that is what prey animals do when threatened, but there is nowhere to run to. The heat is everywhere. The falling ejecta is everywhere. The darkness beginning to gather at the edges of the sky is everywhere. Some predators, operating on instinct, attack nearby prey animals, as if killing and eating now matters, as if tomorrow will ever come. But increasingly, predator and prey alike simply stand confused, overwhelmed by stimuli their evolution never prepared them for, waiting for something to make sense again. It will not. Above the impact site, something visible from space is forming. A plume of vaporized rock and superheated gas rises through the atmosphere, punching through the stratosphere and reaching into space itself. This plume is visible from thousands of kilometers away, a pillar connecting Earth to the heavens, glowing with the heat of the impact. Material in this plume will spread through the upper atmosphere, beginning the process of global darkness that will last for months or years. But in these first minutes and hours, the immediate effects dominate. The sonic boom continues circling the planet, refracted and reflected by the atmosphere, creating secondary shocks that arrive unexpectedly in regions that have already experienced the initial wave. The seismic waves travel through Earth's crust, causing earthquakes thousands of kilometers away, triggering landslides and volcanic eruptions that add their own contributions to the gathering catastrophe. And through it all, across the planet, dinosaurs are dying. Not all of them yet. Not even most of them yet. But millions are already gone, and millions more are fatally injured, their deaths certain even if delayed. The extinction has begun, and nothing can stop it now. The age of dinosaurs is ending, not gradually over millennia, not with any chance to adapt or migrate or evolve, but in fire and violence and darkness, in an afternoon that has become apocalypse, in hours that will echo through 66 million years. The fire raining from the sky is only the beginning. While dinosaurs across the globe struggle with heat and darkness and falling debris, something even more catastrophic is building at the impact site. The asteroid struck in shallow ocean, and now the displaced water is returning with apocalyptic fury. Within seconds of impact, the ocean was pushed aside, creating a temporary void hundreds of meters deep and hundreds of kilometers wide. But water, obeying gravity and pressure, cannot remain displaced. It rushes back toward the impact crater from all directions, colliding with itself and rebounding outward as waves. These are not normal waves. These are mega-tsunamis, walls of water over 1 kilometer high, carrying the kinetic energy of the impact itself, racing outward from ground zero at speeds exceeding 800 kilometers per hour. They are moving mountains of water, and nothing in their path will survive. The first land to experience these tsunamis is the coastline of what will become the Gulf of Mexico. Coastal regions here host rich dinosaur populations, attracted by abundant vegetation, fresh water sources, and diverse prey animals. Hadrosaurs nest in colonies numbering thousands. Tyrannosaurs patrol hunting territories. Smaller dinosaurs fill every ecological niche, from shoreline scavengers to forest browsers. They have perhaps 10 minutes warning. The warning is meaningless when there is nowhere to flee. The water along the coast recedes dramatically as the approaching wave draws water into itself, exposing hundreds of meters of seafloor. Fish flop helplessly on suddenly exposed ground. Marine creatures that have never seen air die in the sun. Some dinosaurs, curious or confused, walk onto the exposed seafloor, investigating this strange phenomenon. They are still there when the wave arrives. The tsunami hits the coast like a solid wall. Not a breaking wave, but a vertical wall of water moving at incredible speed. It does not wash onto the beach. It obliterates the beach, the coastal plain, everything for hundreds of kilometers inland. The wave is so tall that it overtops cliffs and hills that would normally provide safety. The force is so immense that it scours the landscape to bedrock, stripping away soil and vegetation and every living thing, leaving only bare rock. Dinosaurs caught in this maelstrom are torn apart by the sheer force of the water, their bodies tumbling through the surge like leaves in a hurricane. Some are driven kilometers inland and deposited in forests that will never see the ocean again under normal circumstances. Others are pulled back out to sea as the water retreats, their bodies joining the chaotic mix of debris, sediment, and shattered ecosystems swirling in the Gulf waters. But the devastation is not limited to the immediate coast. The tsunami penetrates deep inland along river valleys and lowland plains. The Western Interior Seaway, that shallow ocean currently splitting North America into eastern and western continents, becomes a chaos of conflicting waves as tsunamis race up its length from the south. Mosasaurs and Plesiosaurs, the dominant marine predators, find themselves thrown onto land or dragged into freshwater environments where the salinity drops catastrophically. These animals, some weighing several tons and stretching over 15 meters in length, are as helpless as the smallest fish. They are creatures of open water, and when that water becomes a weapon, their adaptations become liabilities. Their bodies will eventually fossilize in landlocked sediments, confusing future paleontologists who cannot understand how marine creatures ended up hundreds of kilometers from any ocean. Across the Atlantic, tsunamis race toward both the African and European coasts. These waves have traveled thousands of kilometers and have diminished somewhat in height, but they still exceed 100 meters when they make landfall. European coastlines host their own dinosaur populations, different species adapted to slightly different climates, but equally unprepared for ocean-scale violence. Abelisaurids and other predators hunt along coastal plains. Herbivorous dinosaurs graze on vegetation nourished by coastal rains. All of them die within minutes of the tsunami's arrival, their bodies swept inland or out to sea, their ecosystems destroyed so completely that survivors, if any exist, will find nothing familiar remaining. The wave crashes into coastal forests with such force that it snaps trees hundreds of years old, creating massive logjams of debris that will eventually fossilize, creating confused sediment layers that record the chaos of this moment. In the Pacific, tsunamis race westward across the vast ocean, their energy gradually dissipating over thousands of kilometers, but still carrying enough force to devastate coastlines when they arrive. Coastal Asia and the islands of the Pacific experience waves tens of meters high hours after the initial impact. Dinosaurs on these shorelines have no warning, no indication that anything unusual has happened half a world away. The sky may seem slightly brighter to the east, the air may carry unusual sounds, refracted by the atmosphere across vast distances, but nothing prepares them for waves that appear from calm seas without the normal precursors of storm or earthquake. One moment the ocean is normal. The next moment it is rising, surging inland with irresistible force, drowning everything in its path. Island populations of dinosaurs, already isolated by water, are completely wiped out as tsunamis wash over entire land masses, leaving nothing but barren rock and scattered debris. Perhaps the most remarkable evidence of these tsunamis will be discovered millions of years later by paleontologists working at a site called Tanis in North Dakota, over 3,000 kilometers from the impact site. This location in the late Cretaceous is at the southern end of the Western Interior Seaway, and when the tsunamis race up this inland ocean, they create a massive siege, a standing wave that sloshes back and forth. The Tanis site preserves a remarkable snapshot of the impact day itself. Paleontologists will find sturgeon and paddlefish fossils with impact spherules, tiny glass beads formed from vaporized rock lodged in their gills. These fish were alive when the spherules fell from the sky, inhaling them in their final minutes of life. The sediment layers show multiple surges of water arriving in waves, each depositing distinctive layers of material. Amber preserves insects and plant material from that exact day. The site is a time capsule, a frozen moment that captures not the impact itself, but its immediate aftermath, the chaos of water and debris and dying ecosystems preserved in perfect detail. The tsunamis also affect dinosaurs far from coasts in unexpected ways. When massive amounts of water are displaced and then surge inland, they disrupt freshwater systems hundreds of kilometers from any ocean. Rivers reverse their flow temporarily as tsunami waters push upstream. Lakes overflow their banks as displaced water finds new channels. Wetland ecosystems, carefully balanced between land and water, are destroyed completely as saltwater mixes with fresh, killing freshwater species and contaminating drinking sources. Dinosaurs dependent on these water sources find them suddenly poisoned or simply gone. A Triceratops approaching its regular watering hole finds only churned mud and dead fish. A group of young Hadrosaurs, separated from adults during the initial earthquake and thermal pulse, reaches a river only to find it flowing backward, its water murky with sediment and undrinkable. These indirect effects extend the reach of the impact far beyond the obvious zones of destruction. The water that surges inland must eventually return to the ocean, and when it does, it creates secondary catastrophes. The retreating water carries with it everything not permanently anchored: soil, vegetation, trees, and countless bodies of dead or dying animals. This creates a massive debris flow, a slurry of destruction that scours channels and deposits chaotic sediment layers that will preserve a remarkable but disturbing record. Dinosaurs that survived the initial tsunami by reaching high ground are often caught by the retreating water, their footing undermined as the ground itself liquefies and flows seaward. They tumble into the surge and are carried away, their bodies eventually depositing in offshore sediments where they will fossilize alongside marine creatures, creating fossil assemblages that mix terrestrial and marine species in ways that would never occur naturally. These mixed fossil beds will provide future scientists with important evidence about the impact's immediate effects, showing that the catastrophe affected both land and sea simultaneously. By the end of the second hour after impact, the major tsunamis have reached most coastlines in the Atlantic and Pacific basins. The water has penetrated as far inland as it can, has deposited its deadly cargo of debris and destruction, and is beginning to retreat. The immediate coastal devastation is complete. Every dinosaur within 100 kilometers of pre-impact coastlines is dead, buried, or swept out to sea. Every coastal ecosystem is destroyed, scoured to bedrock, or buried under meters of chaotic sediment. The nesting colonies of hadrosaurs are gone without a trace. The coastal hunting grounds of Tyrannosaurs are unrecognizable wastelands. The rich biodiversity of shoreline environments, built over millions of years of evolution, has been erased in less time than it takes the sun to move noticeably across the sky. And this is still only the beginning. The tsunamis were the second wave of destruction, following the immediate effects of impact but preceding something even more insidious. Because while water can kill quickly and obviously, what is gathering in the atmosphere will kill slowly and thoroughly, targeting not just individuals or populations, but entire ecosystems, the very foundation of life on Earth. The darkness is coming, and when it arrives, the real extinction will begin. As the waters retreat and the coastlines settle into their new configurations of devastation, survivors might believe the worst has passed. they would be catastrophically wrong. Above them, invisible in the chaos and dust, millions of tons of material launched into space during the impact are beginning their return journey. The ejecta curtain, that debris field of vaporized and molten rock thrown beyond the atmosphere, has reached the apex of its ballistic trajectory and is now falling back to Earth. These fragments, ranging from microscopic particles to boulders the size of buildings, begin re-entering the atmosphere across the entire planet, and as they do, they transform the sky into a furnace. Each piece of debris, traveling at orbital velocities of several kilometers per second, compresses the air ahead of it, generating tremendous friction and heat. The fragments glow white-hot, becoming meteors, and suddenly the entire sky is filled with billions of meteors simultaneously. It is a sight no dinosaur has ever witnessed, a phenomenon beyond anything in their evolutionary experience, and it is lethal. The thermal radiation from this global meteor shower begins heating the atmosphere in ways that seem impossible. The air itself becomes hot, not from direct sunlight, but from the radiant energy of billions of incoming fragments. In some regions, particularly those with direct line of sight to the impact site, where the densest concentration of ejecta falls, air temperatures spike to 200 degrees Celsius or higher. This is beyond what any large land animal can survive. Dinosaurs caught in these thermal zones experience something worse than fire. Fire can be fled, can be avoided by seeking water or bare ground. But when the air itself becomes an oven, there is no escape. Their respiratory systems are designed for breathing air at reasonable temperatures. When they inhale superheated air, it sears their lungs, causing immediate damage that leads to suffocation even if the external heat doesn't kill them first. Smaller dinosaurs with higher metabolic rates and smaller body masses die within minutes, their internal temperatures spiking beyond what their biochemistry can tolerate. The debate about whether a true global firestorm ignited will occupy scientists for decades after the impact's discovery. But for the dinosaurs living through these hours, the distinction is academic. Whether every forest on Earth caught fire simultaneously or fires remained regional doesn't matter to the individual animal watching its world burn. What is certain from geological evidence is that massive fires erupted across North America and other regions. The combination of thermal radiation from falling ejecta, lightning from atmospheric disruption, and already stressed vegetation from years of Deccan Traps volcanic activity creates perfect conditions for conflagration. Forests that have stood for millions of years ignite within hours. The fires spread rapidly, driven by winds generated by the temperature differentials from the impact. Dinosaurs flee before walls of flame, their panic overriding their normal territorial behaviors, predator and prey, running side by side in desperate attempts to outrun destruction. The Tyrannosaurus matriarch from Montana, thrown to the ground by the initial earthquake, has struggled to her feet and is attempting to navigate a landscape that no longer makes sense. The familiar forest she has hunted for decades is transformed. Half the trees are down, creating impassable tangles of fallen trunks. The sky, which cleared briefly after the initial brightness, is darkening again, but this time with something more sinister than normal clouds. The horizon glows orange in multiple directions. She can smell smoke, acrid and thick, carried on hot winds that shift direction chaotically. Her ears, damaged by the sonic boom but still partially functional, detect sounds of other animals crashing through the undergrowth. Fleeing she knows not what. Her instincts tell her to find water, to seek the river valley where she began this terrible day. But when she reaches what should be the river, she finds it choked with debris and dead fish, the water murky and steaming. She drinks anyway because thirst is becoming unbearable. The water tastes wrong, metallic and bitter, contaminated by fallout already settling from the atmosphere. Across the Pacific in what will become Asia, different species face their own versions of hell. A herd of Hadrosaurs, plant eaters with complex social structures and sophisticated communication abilities, huddles in a valley surrounded by burning hillsides. They have instinctively sought low ground, which protects them somewhat from the worst of the thermal radiation, but they are trapped. The fires on the ridges above them are creating their own weather, generating winds that swirl and shift unpredictably. Burning embers rain down on them constantly. Some of the younger animals, their skin already burned from the earlier thermal pulse, are in severe distress. The adults attempt to shield them with their own bodies, but there is no real protection to offer. The herd stays together because that is what herds do, because their entire evolutionary strategy depends on group cohesion. But for the first time in their species' history, staying together offers no safety. There is no safety anywhere. Flying reptiles, the pterosaurs who have ruled the skies for over 150 million years, find their mastery of the air has become a death sentence. The atmosphere is in chaos, with temperature inversions and pressure differentials creating turbulence beyond anything they have evolved to handle. The hot air rising from fires generates updrafts powerful enough to throw even the largest pterosaurs thousands of meters upward uncontrollably. Others attempting to fly encounter pockets of superheated air that sear their delicate wing membranes. The membranes, stretched thin to minimize weight and maximize lift, offer no protection against heat. They blister and tear, rendering flight impossible. Pterosaurs that lose flight ability at altitude plummet to their deaths, their bodies impacting with force that shatters their hollow bones. Those grounded by injury or caution find themselves vulnerable to fires and ground-level hazards they normally avoid by staying airborne. A Quetzalcoatlus, one of the largest flying animals ever to exist with a wingspan exceeding 10 meters, attempts to launch itself from a cliff to escape approaching flames. Its burned wings fail to generate sufficient lift. It crashes halfway down the cliff face, its neck snapping on impact, ending a lineage that survived since the Triassic. The smaller dinosaurs, those turkey-sized and below, face a different calculus of survival. Their small body mass means they heat up rapidly and cannot buffer against temperature spikes, but it also means they need less food, less water, and can hide in spaces too small for larger animals. Some of them instinctively seek burrows, either their own or commandeered from mammals, and disappear underground where temperature remains more stable and air remains breathable. Others seek refuge in water, diving beneath the surface where liquid absorbs the worst of the thermal radiation. These survival strategies, employed desperately without understanding, will determine which lineages persist. The dinosaurs that happen to engage in burrowing or aquatic behaviors survive these crucial hours in disproportionate numbers. Later, when paleontologists examine the fossil record of species that survived past the KPG boundary, they will notice this pattern. The survivors were small, often burrowers, often omnivores capable of eating whatever food sources persisted. The specialists, the large-bodied, the obligate carnivores and herbivores with narrow dietary requirements, they are dying now in vast numbers. The herbivore herds, those massive aggregations of plant eaters that dominated Cretaceous ecosystems, are breaking apart under pressures their social structures cannot accommodate. A Triceratops herd that numbered hundreds at dawn has scattered, fragmented by earthquakes, fires, and blind panic. Individual animals roam landscapes they no longer recognize, calling for herd mates who cannot hear or cannot respond. Some Triceratops, injured by falling trees or trampled in earlier stampedes, lie dying alone, their massive frills and horns offering no defense against invisible atmospheric threats. Others, still mobile but disoriented, walk in circles or charge at perceived threats that don't exist, their brains scrambled by heat stress and trauma. The largest individuals, those multi-ton bulls who dominated herd hierarchies through size and strength, are discovering that body mass which intimidated rivals offers no advantage against environmental catastrophe. In fact, their large size works against them now, requiring enormous quantities of water and food that are no longer available. As the 4th and 5th hours after impact pass, the atmospheric changes accelerate. The ejecta falling from space begins to include finer particles, dust-sized fragments that don't burn up completely during re-entry, but instead settle gradually through the atmosphere. This dust is different from normal atmospheric particulates. It is impact-generated, consisting of vaporized and recondensed rock, exotic minerals formed under the extreme pressures and temperatures of impact, shocked quartz crystals with distinctive fracture patterns that occur only in impact or nuclear events. This dust begins to form a global aerosol layer, suspended in the stratosphere where weather cannot remove it quickly. As it accumulates and spreads, it starts to block sunlight. The sky, which has been lurid with firelight and glowing with falling ejecta, begins to darken with something more ominous. It is not the darkness of night, which brings coolness and relief. It is the darkness of extinction, and it will last far longer than any night. The impact has also injected massive quantities of sulfur into the atmosphere. The Yucatan Peninsula's bedrock contained extensive sulfate deposits, and the impact vaporized millions of tons of this material. In the atmosphere, sulfur dioxide combines with water vapor to form sulfuric acid aerosols. These tiny droplets, suspended high in the atmosphere, create a reflective layer that further blocks sunlight while also beginning to fall as acid rain. The rain, when it comes in subsequent hours and days, will be corrosive enough to burn exposed skin and poison water sources. Plants already stressed by heat and fire will be unable to tolerate the acidity. The ocean's surface layers will acidify, killing phytoplankton and beginning the collapse of marine food chains. But these effects will unfold over days and weeks. For now, in hours 4 through 6, the immediate threat remains the fires and the heat and the gathering darkness. Our Tyrannosaurus matriarch, having drunk contaminated water and found no food, makes a decision shaped by millions of years of predator evolution. She begins tracking wounded prey, following the scent of blood and injury. In normal times, this would be a successful strategy. Wounded animals are easy kills, providing food for minimal effort. But these are not normal times. She finds a dying hadrosaur, its body burned and broken, lying in a clearing. She approaches cautiously, but the hadrosaur doesn't flee or defend itself. It is too far gone. She kills it quickly, efficiently, ending its suffering while securing food. She feeds, tearing flesh from the carcass, driven by hunger that has become acute. But even as she eats, she is dying. The thermal damage to her lungs is irreversible. The contaminated water has introduced toxins her body cannot process. The psychological stress of the day's events has pushed her endocrine system beyond its capacity to regulate. She will survive perhaps another day, maybe 2 if she is exceptionally strong. But she will not see another sunrise that looks like the one that began this morning. The sun, when it rises tomorrow, will be dim and red, filtered through layers of dust and aerosols. And the morning after that, it may not be visible at all. The fires continue burning as the 6th hour passes, their light now providing the primary illumination across much of the planet. But even this terrible brightness is beginning to fade, not because the fires are diminishing, but because something is eclipsing them. The dust and aerosols suspended in the upper atmosphere have reached critical concentration. What began as a slight dimming of sunlight has accelerated into something far more ominous. The sky, visible between smoke from ground-level fires, is no longer blue or even gray. It has taken on a sickly brown-red color, the sunlight scattered and absorbed by trillions of tons of suspended particles. And with each passing minute, less sunlight penetrates to the surface. 15 trillion tons of pulverized rock, vaporized seafloor, and impact-generated compounds now form a global shroud, a blanket of debris that is transforming day into twilight. For species that have lived under bright tropical sun for their entire evolutionary history, this gathering darkness is as alien and threatening as the fires and earthquakes that preceded it. The temperature effects are immediate and devastating. The same atmosphere that heated catastrophically during the thermal pulse hours earlier is now cooling with equal rapidity. Sunlight, which has warmed Earth's surface for 4 billion years, is being blocked with 99% efficiency. The heat radiating from fires provides local warming, but fire is patchy, and much of the planet's surface is beginning a temperature crash unlike anything in recent geological history. Within these 6 hours, global average temperature has dropped 10 degrees Celsius. By hour 12, it will drop another 10 degrees. Regions that experienced tropical warmth this morning are approaching temperate zone temperatures by evening. And this is just the beginning. The dust will remain suspended for months, possibly years, and during that time, temperatures will continue falling. Ice Age conditions will develop in regions that have never known frost. Dinosaurs, whether they maintained fully warm-blooded metabolisms or were mesothermic with temperature-dependent activity levels, evolved in a hothouse world. They have no adaptations for extended cold, no thick fur or hibernation capabilities. The cold will kill as efficiently as the heat did, just more slowly. But before the cold can kill, there is another catastrophe unfolding that will prove even more fundamental. Photosynthesis, the process that has powered terrestrial ecosystems for hundreds of millions of years, is grinding to a halt. Plants require light to convert carbon dioxide and water into the sugars that fuel their growth and that feed every herbivore on the planet. As light levels drop below critical thresholds, plants stop producing energy. They begin consuming their stored reserves instead, essentially eating themselves to stay alive. For annual plants and small vegetation, these reserves last days or weeks at most. For large trees with extensive root systems, the reserves might sustain them for months. But make no mistake, without photosynthesis, every plant on Earth is on a timer, living on borrowed time while its stored energy depletes. And when the plants die, everything that depends on them dies too. The food chain is collapsing from the bottom up, and there is nothing any animal can do to stop it. The surviving dinosaurs at hour 6 are operating in states of severe stress and confusion. Their world has become unrecognizable. The familiar landmarks they use for navigation are obscured by smoke and failing light. The temperature is swinging wildly between the residual heat from fires and the cooling caused by blocked sunlight. Their water sources are contaminated or destroyed. The air quality is deteriorating rapidly as smoke and dust particles fill the lower atmosphere. Many dinosaurs are experiencing respiratory distress, coughing and wheezing as their lungs struggle to extract oxygen from air thick with particulates. Their eyes burn from smoke and acidic compounds. Their injuries from the earlier earthquakes and thermal pulses are becoming infected, their immune systems compromised by stress. They are hungry, but finding food in the darkness and chaos is nearly impossible. Even the carnivores, who might expect to benefit from the abundance of dead and dying prey, are struggling because the carcasses are often burned beyond palatability or buried under debris. In what will become Asia, a different drama is unfolding. Here, the Deccan traps have been erupting for millennia, and local dinosaur populations have already adapted somewhat to volcanic activity and reduced air quality. These populations might have a marginal advantage in dealing with smoke and ash, their respiratory systems perhaps slightly more tolerant of particulates. But this advantage is tiny and ultimately meaningless. The scale of the current catastrophe dwarfs anything the Deccan traps produced. The darkness descending is global and absolute. The temperature drop is beyond anything volcanic winter produced. These dinosaurs will die alongside their counterparts on other continents, their minor adaptations overwhelmed by major catastrophe. A herd of Titanosaurs, those largest of all dinosaurs, with necks reaching into the canopy, finds that the canopy itself is dying. The leaves they feed on are wilting, stressed by heat and now by darkness. The Titanosaurs strip what vegetation remains, but there is not enough, and what they consume will not be replaced. The marine ecosystems are experiencing their own collapse, different in details but equally catastrophic in outcome. The ocean surface, which received massive injections of energy during the impact and tsunamis, is now cooling as sunlight disappears. But more critically, the base of the marine food chain is dying. Phytoplankton, microscopic photosynthetic organisms that have formed the foundation of ocean ecosystems for hundreds of millions of years, require sunlight just as terrestrial plants do. As light penetration into water drops to near zero, phytoplankton stop reproducing. Within days, their populations will crash. Zooplankton that feed on phytoplankton will starve. Small fish that feed on zooplankton will starve. The cascade will work its way up through every level of marine food webs until even the apex predators, the Mosasaurs and sharks and other large predators, find themselves in an ocean that can no longer support them. The deep ocean ecosystems around hydrothermal vents, which rely on chemosynthesis rather than photosynthesis, will survive this extinction. But the surface ocean and coastal ecosystems, where diversity and productivity are highest, are doomed. Acid rain begins falling during these hours, adding another layer of misery to the catastrophe. The sulfuric acid aerosols forming in the upper atmosphere eventually become too concentrated and heavy to remain suspended. They fall as rain with pH levels far below normal, sometimes approaching the acidity of battery acid in extreme cases. This rain burns exposed skin on contact, causing pain and damage that further stresses already traumatized animals. More insidiously, it poisons water sources. Streams and lakes that survived the tsunamis and fires now become acidified beyond what most aquatic life can tolerate. Fish die by the millions, their gills corroded by acid. Amphibians, with their permeable skin, are among the first to succumb. Even dinosaurs drinking from these contaminated sources are poisoning themselves, ingesting water that their bodies cannot process without damage. Some recognize that the water is wrong and refuse to drink, but thirst eventually overrides caution, and they drink anyway, choosing slow poisoning over certain dehydration. As hour 12 approaches, the last vestiges of daylight are disappearing. In regions not obscured by local smoke and fire, the sun, when it sets, is a dim red disk, barely visible through the atmospheric haze, providing almost no warmth or useful light. When it disappears below the horizon, the darkness that follows is profound. This is not the comfortable darkness of normal night, which brings cooler temperatures but also brings stars and moonlight, which brings nocturnal ecosystems to life. This is the darkness of extinction, complete and smothering. The stars are invisible, hidden behind the dust veil. The moon, when it rises, provides only the faintest glow. Not enough to see by, not enough to navigate by. Dinosaurs that have relied on vision for hunting or avoiding predators are effectively blind. Those species with good night vision have a marginal advantage, but even they struggle in near total darkness. The nocturnal mammals, those small, scurrying ancestors of ours who have always lived in darkness, find conditions less alien than the dinosaurs do. They have always been active at night, have always navigated by sound and smell more than sight, have always lived in burrows where light was absent. The darkness does not frighten them. The chaos does. The fires and earthquakes certainly do. But the darkness itself they can handle. They emerge from their burrows cautiously, testing the air, finding it acrid but breathable. They discover an abundance of food they have never experienced before. Dead and dying animals everywhere, carcasses that would normally be claimed by large scavengers, but now lie undefended because the large scavengers are themselves dead or dying. These mammals feed cautiously and quickly, then retreat to their burrows, where temperature remains more stable and air quality is slightly better. They are not thriving, but they are surviving, and survival is the only currency that matters now. Birds, or rather the small dinosaurs that will eventually be classified as birds, face a complex calculus of survival. They are dinosaurs, sharing the same basic physiology and evolutionary history as their larger relatives. But they possess several crucial advantages. Their small body size means low food requirements, allowing them to survive on seeds and insects and small prey when larger animals starve. Their feathers provide insulation against the cooling temperatures, a feature that evolved for display and flight but now serves a survival function. Their higher metabolic rates and more sophisticated respiratory systems, adaptations for the energy demands of flight, allow them to maintain body temperature more effectively than larger dinosaurs. And perhaps most critically, many bird lineages have already evolved the ability to eat seeds. When all other food sources fail, when insects die and prey animals vanish, and vegetation wilts, seeds will remain, buried in soil, dormant and nutritious, waiting for conditions to improve. The bird species that can exploit this resource will survive. Those that cannot will perish with the non-avian dinosaurs. At the 12-hour mark after impact, perhaps half of all dinosaur individuals are dead. The percentage varies by region and species, but the trend is clear and accelerating. The large herbivores, those multi-ton consumers of vegetation, are dying fastest because their food requirements are enormous and cannot be met in devastated landscapes. The large carnivores are dying nearly as fast because their prey base is collapsing. The medium-sized species of both types have higher survival rates but face the same ultimate doom. Not enough food, not enough clean water, temperatures outside their tolerance range, air quality that damages respiratory systems with every breath. The small dinosaurs, those under 20 kilograms, have the highest survival rates because their needs are modest and their options more varied. They can hide in burrows, can eat a wider variety of foods, can survive short-term deprivation better than large species. But even most of them are doomed because the ecosystem collapse is total, and there is no rebuilding without sunlight. The Earth at midnight of this terrible day is unrecognizable from the Earth that experienced sunrise 12 hours earlier. The climate has shifted from hothouse to impact winter in less than a day. The atmosphere is choked with dust and aerosols that will remain suspended for months or years. Fires burn across multiple continents, consuming forests that have stood since the Jurassic. The oceans are toxic at the surface, their food chains severed at the base. Freshwater sources are contaminated with acid and debris. The plant life that has sustained terrestrial ecosystems for hundreds of millions of years is beginning an inevitable decline into dormancy and death. And across this ruined landscape, dinosaurs wander in darkness and confusion, hungry and cold and injured, unable to comprehend what has happened, unable to adapt to conditions beyond their evolutionary experience, unable to survive what is coming next. The immediate catastrophe of impact and fire and tsunami is over. The long dying, the starvation, and cold and slow extinction is just beginning. And it will last not hours, but months, years, perhaps even decades in isolated pockets where small populations cling to existence before finally succumbing. The age of dinosaurs is ending, and the darkness that has fallen is both literal and metaphorical, a darkness that will persist until the dust settles and the sun returns to a planet that no longer belongs to the giants who once ruled it. The darkness that fell at the end of the first day does not lift with the dawn. When Earth completes its rotation and the sun should rise over Hell Creek or the Gulf Coast or the forests of Asia, there is no sunrise in any meaningful sense. The sky brightens marginally, shifting from absolute blackness to a murky twilight that barely allows vision beyond a few meters. The sun exists somewhere above the dust veil, providing just enough diffuse light to create shadows, but not enough to warm the surface or power photosynthesis. This dim twilight is the new normal, and it will persist not for days, but for months, possibly years. The impact winter has begun in earnest, and with it comes the systematic dismantling of every ecosystem on the planet. The survivors of the first terrible day face a new challenge, one that will prove even more insurmountable than fire and tsunami. They must survive in a world where the fundamental source of energy, the sun itself, has been switched off. By day 2, the plant die-off is already visible to any observer capable of noticing such things. Leaves are wilting across the globe, not from fire or heat, but from simple starvation. Without sunlight, photosynthesis has stopped, and plants are consuming their stored carbohydrates just to maintain basic cellular functions. The smallest plants, those annuals and quick-growing species with minimal energy reserves, are beginning to die. Grasses that covered vast plains are turning brown. Ferns and small shrubs are wilting. Even the great trees, those ancient specimens that have survived storms and fires and previous climate shifts, are beginning to suffer. Their leaves yellow and fall prematurely. Their branches shed unnecessary tissue to conserve energy. The forests that have defined terrestrial landscapes for hundreds of millions of years are entering a dormancy from which many will never awaken. And with each dying plant, the base of the terrestrial food web crumbles further. The herbivorous dinosaurs are the first to experience the full scale of this collapse. These animals, from the massive sauropods requiring hundreds of kilograms of vegetation daily to the smaller ornithopods browsing on shrubs and ground plants, are facing simple arithmetic of starvation. The food they need no longer exists in sufficient quantities. A Triceratops that might normally consume 50 kilograms of vegetation daily finds perhaps 5 kilograms of edible material after hours of searching in darkness. This is not enough to maintain its massive body, let alone provide energy for movement and thermoregulation. The animal begins burning its fat reserves, then muscle tissue, slowly cannibalizing itself to stay alive. Its movements become sluggish as energy depletes. Its immune system weakens, making it vulnerable to infections from injuries sustained during the impact. Within 2 weeks, this once powerful animal is a shadow of itself. Ribs visible through hide, barely able to stand. By day 30, it is dead, one of millions of herbivores that starve in the darkness. The sauropods, those colossal long-necked dinosaurs that include the largest land animals ever to exist, die even faster despite their size. Their enormous bulk requires constant feeding, and their specialized digestive systems are optimized for processing large quantities of low-nutrient vegetation. When vegetation becomes scarce, their survival strategy fails completely. A titanosaur that needs to consume 200 kilograms of leaves daily to maintain its 70-ton body cannot adapt to eating 5 kilograms. The mathematics of metabolism are unforgiving. These giants begin dying within the first week after impact, their bodies too large to hide or hibernate, their food requirements too great to meet in devastated ecosystems. Their massive carcasses become temporary food sources for scavengers, but even scavengers are running out of time. The abundance of carrion is a resource that cannot be replenished, and when it is consumed or rotted, the scavengers too will face starvation. The predatory dinosaurs experience a delayed collapse that is no less inevitable. In the immediate aftermath of impact, carnivores actually have abundant food from the millions of animals killed by trauma, fire, and heat. The Tyrannosaurus matriarch from Montana feeds on these carcasses for several days, her caloric needs met even as her body struggles with injuries and respiratory damage from the first day. Other tyrannosaurs, allosaurs, and smaller predatory species similarly exploit the abundance of dead prey. But this abundance is an illusion of plenty in a dying world. The carcasses rot or are consumed, and no new prey animals are being born to replace them. The surviving herbivores are themselves starving and becoming increasingly scarce. By week 2, predators are competing over dwindling carrion. By week 3, they are attempting to hunt emaciated herbivores that barely provide enough nutrition to justify the energy expenditure of the hunt. By week 4, the predators are starving, their powerful bodies consuming their own muscles, their hunting prowess useless in a world with nothing left to hunt. The marine ecosystems follow a similar trajectory of collapse, but with some important differences. The ocean's thermal mass means temperature changes more slowly than on land, providing some buffer against the rapid cooling. But this buffer is small comfort when the base of the food chain disappears. Phytoplankton, those microscopic photosynthetic organisms that form the foundation of marine productivity, require sunlight penetrating the water column. As the dust veil blocks 99% of sunlight, the water becomes too dark for photosynthesis even at shallow depths. Phytoplankton populations crash within days, their rapid reproductive cycles meaning they have no long-term survival strategy for extended darkness. The zooplankton that feed on them follow within a week, starving as their food source vanishes. Small fish that feed on zooplankton survive perhaps 2 weeks before their populations collapse. The cascade moves up the food chain with mathematical precision, each level surviving slightly longer than the one below it, but ultimately doomed by the same fundamental problem. No sunlight means no energy entering the system. The Mosasaurs, those enormous marine reptiles that have dominated Cretaceous oceans, are among the last marine species to experience the collapse, but are no less vulnerable. These animals sit at the top of marine food webs, feeding on large fish, sharks, and other marine life. For the first few weeks after impact, they notice little difference in their world. The ocean surface may be cooler and darker, but prey remains available. They continue hunting, their powerful jaws and swimming abilities making them formidable predators as always. But as weeks progress, prey becomes scarce. The fish populations they depend on are crashing as the food chain collapse reaches them. The Mosasaurs hunt more desperately, ranging over wider territories, expending more energy for less food. Their large size, which makes them apex predators, becomes a liability when energy is scarce. By day 30, even the most successful Mosasaurs are facing starvation, swimming through oceans that can no longer support large predators, following instincts and migration patterns that now lead nowhere productive. But amid this global catastrophe, pockets of survival persist. Small mammals emerge from their burrows at night, when darkness is no worse than usual for nocturnal species, and scavenge whatever they can find. They eat insects when available, seeds stored in soil, fungus growing on dead wood, carrion, when they can access it before larger scavengers. Their small size means they need relatively little food, and their opportunistic omnivorous diets allow them to exploit whatever resources exist. More importantly, they can enter torpor or hibernation-like states when food is unavailable, reducing their metabolic needs to near zero for days or weeks at a time. This ability, which evolved for surviving normal seasonal food scarcity, now becomes a survival tool for enduring impact winter. These mammals are not thriving, but they are persisting, and persistence is enough. Crocodilians, those ancient reptiles that have survived since the Triassic period, demonstrate another survival strategy. These animals can enter states of profound metabolic suppression, essentially shutting down non-essential functions and surviving without food for a year or more. They sink into rivers and lakes, buried in mud, their bodies cooled by water to temperatures that slow their metabolism to crawls. Their brains enter states barely distinguishable from death, all non-essential neural activity ceased. They breathe perhaps once per hour. Their oxygen needs minimal in this suspended state. The water around them may be contaminated and acidic. The ecosystem may be collapsing. But these creatures have weathered every extinction event for 200 million years through sheer metabolic stubbornness. They will weather this one too, emerging when conditions improve, to find themselves in a world empty of the dinosaurs that once surrounded them. Turtles employ similar strategies, their hard shells providing protection while they bury themselves in mud at the bottom of lakes and ponds, entering brumation states that allow survival without food for extended periods. Salamanders and frogs, being amphibians with aquatic life stages and the ability to absorb oxygen through their skin, survive in water bodies that retain some buffering against temperature extremes. Insects, with their small size and diverse life stages, include species that can survive as eggs, pupae, or dormant adults, waiting out unfavorable conditions. Many aquatic insect larvae persist in streams and lakes, where their life cycles don't depend on terrestrial vegetation. These survival strategies, evolved for entirely different selective pressures, now happen to be exactly what is needed to survive impact winter. Among dinosaurs, only the smallest species have any realistic chance of survival beyond these first 30 days. Bird-like dinosaurs weighing under a kilogram Those species with feathers for insulation and the ability to eat seeds and insects persist in slightly higher numbers than their larger relatives. But even these small dinosaurs are dying in vast numbers. The species that specialized on particular food sources, particular habitats, particular climatic conditions are being winnowed away relentlessly. Only the most generalist, the most opportunistic, the most adaptable have any chance. And even for these survivors, the coming months will test their resilience repeatedly. Because this first month is merely the acute phase of extinction. The chronic phase, the long, slow starvation winter that will last through the rest of the year and into following years, will be even more challenging. By day 30, the transformation is nearly complete. The Earth that experienced sunrise 66 million years ago on that terrible morning is gone. The hothouse climate has been replaced by impact winter. The lush forests have been replaced by landscapes of dead and dying vegetation. The diverse assemblages of dinosaurs have been replaced by scattered, starving remnants. The rich marine ecosystems have been replaced by oceans in collapse. The bright sun-filled days have been replaced by dim twilight darkness. Perhaps 30% of dinosaur species have gone extinct entirely, every individual of certain lineages now dead. Another 50% exist in populations so reduced and stressed that their extinction is merely delayed, not prevented. The remaining 20%, mostly small-bodied generalist species, cling to existence in refuges where conditions are marginally less catastrophic. But even these survivors face months or years of continued hardship. The mass extinction is well underway, and while the most dramatic phase of death and destruction is over, the final outcome is already determined. The age of dinosaurs is ending, and nothing can reverse the cascade of ecosystem collapse now accelerating toward its inevitable conclusion. The darkness will eventually lift, the sun will return, and life will recover. But the dinosaurs, except for their bird descendants, will not be part of that recovery. Their reign is over, ended not by their own failure but by astronomical bad luck, by a mountain of rock from space hitting the one spot on Earth that would maximize global catastrophe. They were successful beyond measure, and it saved them nothing. The survivors who endure past the first month enter a new phase of survival, one that in many ways is more cruel than the immediate violence of Impact Day. The fires have burned out, leaving scorched landscapes where forests once stood. The acid rain has diminished to occasional showers of merely toxic rather than corrosive intensity. The temperature has stabilized at new, much colder levels, no longer dropping precipitously, but settled into a frigid equilibrium that will persist for months. The dust veil remains intact, blocking sunlight with relentless efficiency, casting the world in perpetual twilight. This is the new normal, and those dinosaurs who survived the chaos must now face a slower, more methodical form of extinction. They must outlast the darkness, the cold, and most critically, the complete absence of growing vegetation. And they cannot. The mathematics of survival are simply impossible for large animals in ecosystems with no primary productivity. The large herbivorous dinosaurs are the first entire groups to vanish completely. By month 3 after impact, the last of the sauropods has died. These colossal animals, which have existed in various forms for over 150 million years, which have adapted to every climate change and survived multiple smaller extinction events, which have represented the pinnacle of herbivore evolution, are gone. The last titanosaur dies alone in what was once a lush forest in South America, its body too weakened to stand, its digestive system empty, its enormous heart finally stopping after weeks of starvation. No one witnesses this death. No other titanosaur remains alive to recognize the significance. The species simply ends. Another entry in the growing list of lineages that will never return. The ceratopsians follow shortly after. Triceratops, those iconic horned dinosaurs that have dominated North American ecosystems, die out by month 4. The herds that once numbered thousands are reduced to scattered individuals, then to none. The Hadrosaurs, those diverse duck-billed dinosaurs with their sophisticated social structures and complex vocalizations, persist slightly longer than other large herbivores because some species can eat a wider variety of plant material, including bark and dead vegetation that other herbivores ignore. But wider dietary tolerance only delays the inevitable. By month 5, even the most adaptable hadrosaurs are dead, their populations too small and scattered to maintain breeding populations even if individuals could survive. The ankylosaurs, those heavily armored dinosaurs whose defensive capabilities made them nearly immune to predation, discover that armor means nothing against starvation. The stegosaurs, already in decline before the impact, vanish completely. Every large herbivorous dinosaur lineage, without exception, goes extinct during these months, unable to meet the energy requirements of their large bodies in a world where plants no longer grow. The large predatory dinosaurs follow their prey into extinction with predictable inevitability. The Tyrannosaurs, those apex predators that have dominated food chains across multiple continents, die out between months 3 and 6. The Tyrannosaurus matriarch from Montana, who survived the impact day and fed on carrion for weeks afterward, finally succumbs in month 4. Her body has consumed its fat reserves, then its muscle tissue, breaking down its own structure to fuel basic metabolism. Her injuries from impact day, never properly healed, have become infected. Her respiratory system, damaged by inhaling superheated air and smoke, struggles to extract sufficient oxygen from the cold, dust-laden atmosphere. One morning, she simply does not rise from where she lay down the previous night. Her massive heart beats a few more times, then stops. Her lineage, stretching back millions of years, ends with her. Other tyrannosaur species across North America and Asia follow the same pattern, their populations collapsing as prey disappears, their energy requirements impossible to meet through scavenging alone. The smaller predatory dinosaurs, velociraptors, and their relatives, those agile pack hunters that have filled carnivore niches in diverse ecosystems, persist longer than their larger cousins because their smaller size means lower absolute food requirements. But they too are doomed. By month 8, even these adaptable predators are largely extinct, unable to find sufficient prey in ecosystems that have collapsed completely. A few individuals might persist in isolated refuges where small mammals or other prey remain available, but populations are too fragmented to sustain breeding. The last velociraptor dies in month 10, its stomach empty, its pack members dead weeks earlier, alone in a landscape that no longer contains anything it can successfully hunt. The great predatory lineages of dinosaurs, those diverse and successful groups that have refined hunting to an art form over millions of years of evolution, are gone. But amid this systematic extinction, something unexpected is happening. The darkness is beginning to lift, not completely, but perceptibly. By month 6, the dust veil has thinned enough that sunlight, though still severely reduced, is reaching the surface in slightly higher quantities. The sky remains gray and overcast, but it is gray rather than black, and on clear days, the sun is faintly visible as a pale disk behind the haze. This marginal increase in light is not enough to save the dinosaurs already on the brink of starvation, but it does trigger responses from the dormant plant life. Seeds buried in soil, spores protected in damp environments, root systems of dead trees that retain some vitality, they begin to stir. Ferns, those ancient plants that have survived multiple mass extinctions through their ability to spread via spores and colonize disturbed environments rapidly, are the first to respond. Fern spores that have remained dormant through the darkness begin germinating, sending up small fronds that can photosynthesize even in the dim available light. This fern spike, as paleontologists will later name it, when they discover the sudden abundance of fern spores in sediments dating to the months after impact, represents the first stage of ecosystem recovery. But it comes too late for most dinosaurs. The large species are already extinct or reduced to populations too small to recover. The medium-sized species, those animals weighing between 100 and 1,000 kilograms, are in their final months of survival. A few individuals persist on fern vegetation that is barely beginning to grow, on insects that are slowly emerging from dormancy, on whatever food sources they can locate in damaged ecosystems. But these individuals are scattered, isolated, unable to find mates, doomed even if they could survive personally. By month 12, virtually all medium-sized non-avian dinosaurs are extinct. Their lineages ended not by sudden violence, but by slow attrition, populations whittled away by starvation and cold and simple bad luck until no breeding pairs remain. The survivors, those lineages that will persist through the extinction and into the Paleocene epoch, share certain characteristics that are now proving decisive. Small body size is paramount. Animals weighing less than 20 kilograms have energy requirements low enough that they can survive on minimal food sources. Seeds, insects, small prey, carrion, whatever they can find. Behavioral flexibility is crucial. Species that can eat multiple food types, that can shelter in burrows or caves, that can adjust their activity patterns to changing conditions, have enormous advantages over specialists. The ability to regulate body temperature effectively in cold conditions is vital. Mammals with their fur and high metabolisms, birds with their feathers and efficient respiratory systems, they maintain body temperature far better than large reptilian dinosaurs. And perhaps most importantly, fast reproductive rates allow populations to recover when conditions improve. Species that mature quickly and produce many offspring can rebuild populations from small founder groups, while species with long generation times and few offspring cannot recover from severe bottlenecks. The birds, those small dinosaurs that will eventually be classified separately despite their dinosaurian ancestry, are demonstrating all these survival traits simultaneously. The species that survive are small, most under 1 kilogram, with energy requirements that can be met by eating seeds and insects. Their feathers provide excellent insulation against the cold, allowing them to maintain body temperature even as the global climate cools dramatically. Their sophisticated respiratory systems, more efficient than mammalian lungs, extract oxygen effectively from air that has become oxygen-depleted due to combustion and atmospheric disruption. Most critically, many bird species can eat seeds, and seeds are one of the few food resources that remain abundant and accessible throughout the extinction. Plant seeds, designed to survive dormancy and germinate when conditions improve, are buried in soil across the planet, waiting. Birds that can exploit this resource have a survival advantage that proves decisive. The fossil record being created during these months tells a story that will eventually be read by paleontologists millions of years in the future. The KPG boundary layer, that thin line of sediment marking the transition between Cretaceous and Paleogene epochs, contains distinctive markers of the catastrophe. A spike in iridium concentration, an element rare in Earth's crust but common in asteroids, marks the exact moment of impact. Shocked quartz grains, with distinctive fracture patterns that only form under extreme pressure, are scattered globally in this layer. Spherules of impact glass, formed when vaporized rock cooled rapidly, are preserved in sediments. Above this boundary layer, the abrupt disappearance of non-avian dinosaur fossils is striking. Species that were common and widespread in Cretaceous sediments simply vanish. Their fossils are not found in Paleocene rocks, not because preservation conditions changed, but because the animals no longer existed. The fern spike appears in sediments dating to months after the boundary, a surge in fern spore abundance that indicates ecological disturbance and the beginning of recovery. Then, gradually, new species appear in the fossil record. Small mammals that were rare and insignificant in Cretaceous ecosystems begin diversifying and growing larger. Birds radiate into new forms, filling ecological niches left vacant by extinct dinosaurs. Crocodilians and turtles persist largely unchanged, their survival strategies proving robust. The fossil record shows not just death, but also transformation, the ending of one biological era and the beginning of another. This transition, compressed into months and years from the perspective of geological time, represents one of the most dramatic turnovers in Earth's history, comparable only to the end Permian extinction that preceded the dinosaur age by hundreds of millions of years. By the end of month 12, 1 full year after the impact, Earth is beginning to stabilize into new patterns. The dust veil has thinned substantially, allowing perhaps 20% of normal sunlight to reach the surface. Plants are growing again, slowly and tentatively, but growing. Temperatures are rising from their impact winter lows, though they remain cooler than pre-impact averages. The survivors are beginning to reproduce, cautiously testing whether conditions will support offspring. The non-avian dinosaurs, however, are gone. Perhaps a few isolated individuals persist in remote refuges, clinging to life for another year or two. But they are evolutionary dead ends, unable to find mates, unable to establish breeding populations. The age of dinosaurs is over, ended not in a single terrible day, but through 12 months of systematic ecological collapse, through the slow extinction of every major lineage, as their survival requirements exceeded what devastated ecosystems could provide. They were not weak, they were not failures, they were simply too large, too specialized, too dependent on ecosystems that required sunlight. When the sun disappeared for a year, they disappeared with it, victims of astronomical chance and biological physics, extinct despite 165 million years of evolutionary success. 1 year after impact, Earth is unrecognizable compared to the world that existed before that terrible day. The dust veil, while still present, has thinned enough that sunlight penetrates in meaningful quantities. Plants are photosynthesizing again, tentatively converting sunlight to energy, beginning the slow process of rebuilding terrestrial productivity. But this is not recovery returning to previous conditions. This is something entirely new. The ecosystems that supported dinosaurs for 165 million years are gone, destroyed so completely that they cannot simply regenerate. What emerges from the ruins is different, built on different foundations, dominated by different players. The survivors are inheriting a planet that has been wiped nearly clean, an evolutionary blank slate where the rules have changed and new dynasties can arise. The mammals, those small nocturnal creatures that have lived in dinosaur shadows for over 100 million years, are about to have their moment, and it will last 66 million years and counting. The first decade after impact is a time of tentative exploration and gradual ecosystem assembly. The ferns that emerged during the final months of year 1 continue spreading, their spores colonizing disturbed ground with remarkable speed. Ferns thrive in the aftermath of catastrophe, requiring little soil depth and tolerating poor nutrient conditions, spreading across landscapes like a living bandage over Earth's wounds. But ferns alone cannot support diverse animal communities. Gradually, other plants emerge from dormancy. Flowering plants, which had been diversifying rapidly in the late Cretaceous, begin recolonizing from seeds that survived buried in soil. These angiosperms will eventually come to dominate terrestrial vegetation, but in these early years, they are just one component of recovering plant communities. Conifer trees, which survived better than many other plant groups due to their stress tolerance and long-lived seeds, begin growing again from surviving seedlings and remnant populations. The vegetation returning is patchy and inconsistent, with productive areas separated by barren zones where soil has been stripped away or contaminated beyond immediate recovery. The mammals emerging from burrows and surviving refuges find themselves in a world transformed beyond their evolutionary experience. For over 100 million years, mammals have been constrained by dinosaur dominance, limited to small body sizes and mostly nocturnal lifestyles to avoid competition and predation. But now the constraints are gone. The predatory dinosaurs that would have eaten any mammal larger than a cat are extinct. The herbivorous dinosaurs that would have outcompeted larger mammalian herbivores are gone. The ecological niches for medium and large animals are suddenly vacant, and evolutionary pressure immediately begins selecting for mammals that can exploit these opportunities. Within the first decade, mammal species are already growing larger. Animals that weighed 1 kilogram before the extinction have descendants weighing 5 kilograms. New dietary specializations emerge as different lineages explore different food sources. Some mammals become more herbivorous, developing gut bacteria and dental adaptations for processing plant material. Others become more carnivorous, their teeth and jaws evolving to catch and process meat more efficiently. Birds, those surviving dinosaurs, are experiencing their own radiation into vacant niches. The extinction has eliminated all large and medium-sized dinosaurs, but birds survived because they were already small, already feathered, already capable of eating seeds and insects. Now they diversify rapidly. Flight, which had been just one locomotor strategy among many in the age of dinosaurs, becomes a major advantage in recovering ecosystems. Birds can travel long distances to find productive habitats, can exploit food sources in trees and shrubs that ground-dwelling animals cannot easily reach, can escape ground-dwelling predators that are slowly evolving. Some bird lineages begin growing larger, exploiting size niches no longer occupied by pterosaurs or large non-avian dinosaurs. Others remain small but diversify into thousands of species, each specialized for different food sources and habitats. The remarkable diversity of modern birds, over 10,000 species filling every conceivable ecological role from tiny hummingbirds to massive ostriches, has its origins in this post-extinction radiation. The crocodilians and turtles, those survivors who endured through metabolic shutdown and aquatic refuge, emerge into a world with far less competition than before. Freshwater ecosystems, which recovered somewhat faster than terrestrial systems because aquatic food chains are shorter and can rebuild more quickly, provide habitat for these ancient lineages. Crocodilians in particular benefit from the absence of large predatory dinosaurs. In the Cretaceous, a crocodilian faced competition from numerous large predators, both terrestrial and aquatic. In the Paleocene, they are among the largest predators in many ecosystems, their body plans so perfectly optimized for ambush predation that they require little evolutionary modification. Some crocodilian species even become terrestrial predators, evolving longer legs and more upright postures, filling niches left vacant by extinct theropod dinosaurs. These terrestrial crocodilians will eventually be outcompeted by mammalian predators, but for a few million years, they represent a serious threat to early mammals. Between years 10 and 100, the pace of ecosystem reconstruction accelerates. Soil quality improves as organic matter accumulates from generations of plants and animals living and dying. Forests begin regrowing, though the species composition differs from Cretaceous forests, with flowering plants taking on more dominant roles. Food chains lengthen as primary productivity increases, supporting more trophic levels and more diverse communities. The mammals are growing substantially larger. By year 50, some mammalian herbivores approach the size of large modern deer. By year 100, some species reach the size of horses. This is still tiny compared to the massive sauropods that once existed, but it represents a 1,000-fold increase in body mass from the small insectivorous mammals of the Cretaceous. The evolutionary experimentation happening during these decades is remarkable. Different mammal lineages are trying different survival strategies, different body plans, different dietary specializations. Most of these experiments fail, leaving no descendants, but some succeed spectacularly, founding lineages that will persist for millions of years. The marine ecosystems are recovering along different timelines. The surface oceans, devastated by the collapse of phytoplankton populations, take decades to rebuild productive food webs. But the deep ocean, which maintained chemosynthetic ecosystems around hydrothermal vents throughout the extinction, serves as a refuge from which recolonization can occur. Fish populations slowly rebuild from survivors, though many Cretaceous fish groups went extinct and are replaced by different lineages in the Paleocene. The marine reptiles, the Mosasaurs and Plesiosaurs that dominated Cretaceous oceans are completely gone. They leave no descendants, no close relatives to evolve and fill their niches. Instead, mammals begin exploring marine environments. The ancestors of whales, dolphins, and seals are still fully terrestrial during these early centuries, but the evolutionary pressures that will eventually drive them into the oceans are already present. The ocean contains abundant food and few large predators, creating opportunities for any animal that can exploit them. Between years 100 and 1000, the New World Order establishes itself firmly. Mammals have diversified into most major lineages that will persist to modern times. The primates emerge, small arboreal insect eaters that will eventually give rise to monkeys, apes, and humans. The ancestors of ungulates appear, herbivorous mammals that will diversify into everything from horses to whales. The carnivorous mammals split into multiple lineages, some becoming the ancestors of modern carnivores like cats and dogs, others representing extinct experimental groups. By year 1000, the largest land mammals are approaching the size of modern rhinoceros, a remarkable achievement given that their ancestors 1,000 years earlier were rat-sized. This rapid size increase, driven by the availability of ecological niches and abundant plant food, demonstrates the explosive potential of evolutionary radiation when constraints are removed. The planet's climate during these centuries is warmer than immediately after impact, but cooler than the late Cretaceous hothouse. The impact winter has long since ended, but the redistribution of carbon dioxide and the changes in atmospheric composition mean temperatures stabilize at new levels. The absence of massive herbivorous dinosaurs may itself contribute to climate differences. When sauropods and other large herbivores consumed vast quantities of vegetation and released it as methane through digestion, they contributed to greenhouse warming. Without them, atmospheric chemistry differs subtly. The forests regrowing are different in structure and composition from Cretaceous forests, potentially affecting how much carbon is stored in wood and how much is released through decomposition. These differences, while small compared to the catastrophic changes during impact winter, may contribute to the cooler Paleocene climate compared to the hot Cretaceous. The fossil record preserves this recovery in remarkable detail for those who know how to read it. The Paleocene epoch rocks show gradual increases in mammal diversity and body size, documented through thousands of fossil specimens from sites around the world. The early Paleocene fauna looks alien, filled with mammals that belong to extinct groups with no modern representatives, evolutionary experiments that briefly flourished before being replaced by more successful lineages. Later Paleocene faunas begin showing mammals that look more familiar, early representatives of groups that persist today. The plant fossil record shows similar patterns of recovery, with fern-dominated assemblages giving way to more diverse plant communities, including numerous flowering plant species. Marine fossils show similar recovery patterns, with early Paleocene oceans hosting lower diversity than late Cretaceous seas, but gradually accumulating species as ecosystems rebuild. What becomes clear from examining this recovery is how completely the extinction reset the evolutionary playing field. The dinosaurs didn't fail. They were successful beyond measure, dominating terrestrial ecosystems for over 160 million years, far longer than mammals have dominated so far. They evolved incredible diversity, from tiny bird-like forms to the largest animals ever to walk on land, from speedy predators to armored herbivores to flying forms that challenged the physics of flight. They survived multiple extinction events and climate changes, adapting to shifts that killed many other lineages. Their extinction was not evolutionary failure, but astronomical bad luck, being too large and too dependent on sunlight when an asteroid turned off the sun for a year. The mammals inherited Earth not because they were superior, but because they were small enough and flexible enough to survive what the dinosaurs could not. By year 1000, approximately 65 million years before humans will appear, Earth has transformed completely from the planet the last dinosaurs knew. The hothouse climate is gone, replaced by cooler conditions with ice beginning to form at the poles for the first time in millions of years. The forests are unrecognizable, dominated by flowering plants rather than the conifer and fern mixtures of the Cretaceous. The animals filling these forests are entirely different. Mammals and birds, where once dinosaurs ruled absolutely. The food chains are shorter, with no animals approaching the size of large sauropods, though this will change in future epochs as mammals continue growing. The oceans host fish and marine mammals where once mosasaurs and plesiosaurs hunted. The skies belong entirely to birds, the pterosaurs gone without replacement. It is a new world built on the ruins of the old, and it will continue evolving for millions more years, eventually producing primates, then apes, then humans who will discover the fossils of dinosaurs and piece together the story of what happened on that terrible day 66 million years earlier. The age of dinosaurs is truly over, but life continues, adapts, evolves, fills the emptiness, and flourishes once again. The recovery of life after the extinction raises a question that will fascinate scientists for centuries. Why did some lineages survive while others perished? The answer reveals fundamental principles about extinction, adaptation, and evolutionary success that extend far beyond the specific case of dinosaurs. When we examine the survivors closely, patterns emerge with stark clarity. Small body size was the single most important predictor of survival across almost every animal group. Animals weighing less than 25 kilograms had survival rates dramatically higher than larger species. This wasn't coincidental. Small animals require less food, can hide in protective microhabitats like burrows or hollow logs, can survive on diverse food sources that larger specialists cannot exploit, and can maintain populations from small founder groups because they reproduce quickly. The math of metabolism is unforgiving. A mouse-sized mammal needs perhaps 10 grams of food daily, while a Triceratops needed 50,000 times more. When food became scarce, this difference meant survival versus starvation. Dietary flexibility was equally critical. Animals that could eat multiple food types, switching between insects, seeds, carrion, and plant material as availability changed, survived at much higher rates than specialists. The herbivores that could only digest specific plants died when those plants vanished. The carnivores that specialized on particular prey died when those prey went extinct. But the opportunistic omnivores, those animals that would eat anything remotely digestible, found enough sustenance to persist through the darkest months. This explains why mammals, mostly omnivorous or insectivorous, survived better than large herbivorous and carnivorous dinosaurs. It explains why crows and ravens, omnivorous birds, have thrived while specialized seed-eaters struggled. Evolutionary specialization, which brings efficiency under stable conditions, becomes a death sentence when conditions change catastrophically. The generalists, less efficient but more flexible, inherit the devastated world. Burrowing behavior provided enormous survival advantages that become obvious only in hindsight. Animals that lived underground or could retreat to burrows escaped the worst of the thermal pulse on impact day, avoiding the radiant heat that killed surface-dwelling animals. They escaped the wildfires that consumed forests. They avoided the temperature extremes of impact winter, residing in soil where temperature remained more stable. They breathed air filtered through soil rather than the dust and smoke-laden atmosphere above ground. The fossil record shows this pattern clearly. Burrowing mammals and small reptiles survived at high rates, while surface-dwelling species of similar size died in larger proportions. This wasn't because burrowers were inherently superior organisms, but because they happened to possess a behavior that accidentally protected against a threat they had never encountered before. Evolution cannot plan for asteroid impacts, but animals with traits that happen to be useful during such events survive to pass those traits forward. Temperature regulation capability separated survivors from victims in ways that reflect fundamental physiology differences. Mammals and birds, with their endothermic metabolisms and insulation, could maintain body temperature even as global temperatures plunged during impact winter. Dinosaurs, whether fully warm-blooded or mesothermic, evolved in a hothouse world and possessed no adaptations for extended cold. Their physiology was optimized for tropical and subtropical conditions that no longer existed. When temperatures dropped 30 degrees below pre-impact averages and stayed there for months, even the largest dinosaurs could not generate or retain enough heat. The small mammals in their fur coats, the birds in their feathered insulation, They shivered and suffered but maintained core temperature within survivable ranges. The dinosaurs, lacking equivalent insulation and evolved for warmth, simply froze. This explains why crocodilians, which can enter torpor and don't need to maintain high body temperatures, survived while dinosaurs did not. It wasn't about being reptiles versus mammals, but about having physiologies that could handle extreme cold or shut down temporarily until conditions improved. Aquatic lifestyles provided another survival pathway, particularly for animals that could tolerate low oxygen and could fast for extended periods. Water buffered against temperature extremes, staying liquid even when air temperatures dropped below freezing. Aquatic food chains, while disrupted, recovered faster than terrestrial ones because they were shorter and less dependent on sunlight penetrating through dust veils. Fish could eat organic matter settling from surface waters. Aquatic insects could survive as larvae or eggs. Amphibians could retreat to pond and stream bottoms in dormant states. The crocodilians and turtles that survived the extinction were almost exclusively aquatic or semi-aquatic species. The fully terrestrial species in both groups went extinct alongside the dinosaurs. Similarly, while terrestrial birds suffered extensive extinctions, aquatic and shorebirds survived at higher rates because coastal and wetland habitats recovered somewhat faster than forests and plains. Fast reproductive rates allowed surviving species to rebuild populations quickly when conditions improved. Species that matured in 1 year and produced many offspring per breeding season could recover from population bottlenecks that would doom species with longer generation times. Mammals typically produce multiple offspring per year and reach reproductive maturity within 1 to 3 years, even in larger species of this era. Birds similarly reproduce quickly. Dinosaurs, based on growth rate studies of fossils, took years to reach maturity even in smaller species, and large species required a decade or more. When populations crashed, the mammals and birds could rebuild within a few generations, while dinosaurs would need decades, assuming breeding pairs could even find each other in devastated landscapes. This reproductive difference, seemingly minor under stable conditions, became decisive during the recovery period. The ability to quickly exploit improving conditions and rebuild population numbers meant some lineages thrived while others stagnated. The survivors also shared an often overlooked trait: evolutionary flexibility. The mammal and bird lineages that persisted through the extinction were not highly specialized in terms of body plan or ecological niche. They were relatively generalized in their anatomy, capable of being modified by evolution in multiple directions. This flexibility allowed rapid adaptation when new opportunities appeared. Within a few thousand years, mammals began evolving into forms that would have been impossible under dinosaur dominance: larger herbivores, specialized carnivores, tree-dwelling frugivores, aquatic fish eaters. Birds similarly diversified into ecological roles, from tiny insect specialists to large flightless predators. The dinosaurs, by contrast, had spent 165 million years evolving increasingly specialized forms optimized for specific niches. This specialization made them supremely successful under stable conditions, but vulnerable when the environment changed radically. The extinction didn't select for the best adapted organisms. It selected for organisms that could readapt quickly. Geographic location during impact played an underappreciated role in survival. Species living in regions farther from the impact site, particularly in the southern hemisphere, experienced somewhat less severe immediate effects. While the dust veil and darkness were global, the thermal pulse, tsunamis, and most intensive fires affected regions closer to the Yucatan Peninsula most severely. Some dinosaur species in Patagonia or Australia may have survived weeks or even months longer than North American species, though they ultimately went extinct from the same ecosystem collapse. This geographic variation meant that species with wide distributions across multiple continents had more chances for isolated populations to survive long enough to potentially recover. Species restricted to single regions or continents had no such buffer. The mammals, being small and mobile, existed on all continents with diverse populations. Even severe local extinctions left populations elsewhere to recolonize. Some dinosaur groups had similarly wide distributions and still went extinct, suggesting distribution alone wasn't sufficient, but it provided additional chances for survival. The extinction also reveals an important principle about ecosystem structure. The animals that survived were not the dominant species of their ecosystems. They were the marginal players, the understory species living in the shadows of more successful groups. The mammals were ecological bit players in the Cretaceous, constrained to small sizes and mostly nocturnal lifestyles. The birds that survived were small insectivores and seed-eaters, not the larger or more specialized forms. The successful survivors were those that had been barely getting by before the catastrophe, exploiting niches that more dominant species ignored. When the catastrophe removed the dominant players, these marginal species suddenly faced a world with empty niches and reduced competition. Their previous marginality, their evolutionary humility, became an enormous advantage. This pattern appears in other mass extinctions as well. The meek literally inherit the Earth because they possess survival traits that dominant species, optimized for competition under stable conditions, lack. Understanding what survived and why has profound implications for modern conservation biology and for assessing our own species' vulnerability. The survivors weren't the strongest or most intelligent or most numerous. They were small, flexible, omnivorous, and living in protective habitats. These traits have nothing to do with evolutionary sophistication or competitive dominance. A Tyrannosaurus was more intelligent, more powerful, more impressive than any mammal living alongside it, yet the mammal survived and the Tyrannosaurus didn't. This should humble us. Humans are large-bodied specialists requiring extensive resources and infrastructure. We are not small. We cannot burrow. We cannot fast for months. We cannot enter torpor. Under normal conditions, our intelligence and technology make us dominant. But intelligence doesn't prevent starvation when crops fail globally. Technology doesn't help when ecosystems collapse. If a similar catastrophe struck today, an asteroid impact, or supervolcano eruption, or nuclear winter, the survivors might not be humans, but rats and cockroaches, and small opportunistic animals we currently consider pests. The dinosaurs' extinction teaches us that dominance and success under current conditions predict nothing about survival when conditions change catastrophically. We should be humble, should plan for catastrophe, should work to prevent the preventable disasters while acknowledging that some threats, like asteroid impacts, require active defense rather than passive hope. The survivors of the KPG extinction survived not through planning or intelligence, but through accidental possession of traits useful during catastrophe. We have intelligence. The question is whether we'll use it to avoid our own extinction, or whether, like the dinosaurs, we'll be remembered as successful creatures that nonetheless disappeared when conditions changed beyond our ability to adapt. The lessons written in dinosaur bones and impact debris are not relics of an impossibly distant past. They are warnings, instructions, prophecies written in geological language that we are only beginning to understand. The question that should haunt every human who learns about the dinosaur extinction is simple and terrifying. Could it happen again? And the answer, delivered without comfort or qualification, is yes. Absolutely yes. Earth orbits through a cosmic shooting gallery where asteroids and comets follow trajectories determined by gravity and chance. The rock that killed the dinosaurs was not unique. It was merely one of countless objects crossing Earth's orbital path, distinguished only by the catastrophic bad luck of its timing and target location. At this moment, astronomers have cataloged over 30,000 near-Earth objects, asteroids whose orbits bring them close to our planet. Most will never hit us, but some might. The mathematics of orbital mechanics are clear. Given enough time, another impact of similar scale is not just possible, but probable. The only questions are when and whether we will be ready. The threat is not theoretical or distant. In 2013, a meteor approximately 20 meters in diameter exploded over Chelyabinsk, Russia, releasing energy equivalent to 30 Hiroshima bombs. The shockwave injured over 1,500 people, damaged thousands of buildings, and reminded the world that space rocks hit Earth regularly. That meteor was tiny compared to the Chicxulub impactor, a pebble compared to a mountain, yet it caused significant damage and would have been catastrophic if it had struck a major city directly. In 1908, the Tunguska event flattened 2,000 square kilometers of Siberian forest when an asteroid perhaps 60 meters across exploded in the atmosphere. These events, occurring within living memory or just beyond it, demonstrate that asteroid impacts are not ancient history, but ongoing processes. The dinosaurs had no warning, no comprehension of what killed them. We have both warning and comprehension, which creates both an advantage and a responsibility the dinosaurs never faced. Modern astronomy and space science have given humanity something unprecedented: the ability to see extinction coming and potentially prevent it. NASA's Planetary Defense Coordination Office tracks near-Earth objects, calculating their orbits with increasing precision, identifying which ones pose threats decades or centuries in advance. In 2022, humanity achieved something that would have seemed like science fiction a generation earlier. We deliberately changed an asteroid's trajectory. The DART mission, Double Asteroid Redirection Test, slammed a spacecraft into the asteroid Dimorphos at high speed, altering its orbit measurably. The experiment proved that kinetic impactors can deflect asteroids, that we possess the technology to push dangerous rocks onto safer paths, that extinction by asteroid is no longer inevitable if we have sufficient warning. This is revolutionary. For the first time in Earth's 4 billion-year history, a species exists that can defend against asteroid impacts. The dinosaurs were victims of astronomical chance. We need not be, provided we maintain and expand our detection and defense capabilities. But this capability comes with important limitations. We can only deflect asteroids we detect early, preferably decades before potential impact. An asteroid detected months before collision would be nearly impossible to deflect with current technology. We would have warning but not salvation, time to prepare but not prevent. And our detection systems have blind spots. Asteroids approaching from the sun's direction are difficult to spot because we cannot point telescopes directly at the sun for extended periods. Comets from the outer solar system can appear with little warning, their highly elliptical orbits bringing them into the inner solar system rapidly. A comet strike would be even more devastating than an asteroid of similar size because comets travel faster, carrying more kinetic energy. We have taken the first steps toward planetary defense, but we have not solved the problem completely. Continued investment in detection networks, tracking systems, and deflection technologies is not optional. It is an insurance policy for civilization, a hedge against the catastrophe that ended the age of dinosaurs. The survival lessons from the dinosaur extinction extend beyond asteroid defense to encompass broader principles of resilience and adaptation. The survivors were small, flexible, opportunistic, and inhabiting protective environments. What does this mean for modern species facing extinction from human activities? It suggests that large specialists depending on specific habitats are most vulnerable, exactly the pattern we observe in current extinction rates. Elephants, rhinos, tigers, gorillas. These megafauna are exactly the type of animals that would fare worst in sudden environmental catastrophe. Their large size means high resource requirements. Their specialization means inability to shift to different foods or habitats when preferred options disappear. Their slow reproduction means populations recover slowly from crashes. They are dinosaurs in all but name, dominant under current conditions, but vulnerable to rapid change. If we want these species to survive not just current threats but future catastrophes, we need to maintain large populations in diverse habitats with connectivity, allowing migration and genetic exchange. Isolated populations in small reserves repeat the Wrangel Island pattern: temporary survival followed by eventual extinction when disaster strikes. For human civilization, the lessons are equally stark and uncomfortable. We are large-bodied specialists requiring extensive infrastructure and resources. Our food system depends on stable climate, predictable rainfall, and fossil fuel-intensive agriculture. Disrupting any of these foundations endangers food security for billions. Our cities concentrate populations in areas vulnerable to sea level rise, earthquakes, and extreme weather. Our technology gives us dominance and comfort, but also creates dependencies and fragilities. A solar storm disabling electrical grids, a pandemic worse than COVID-19, a nuclear exchange creating even a mild nuclear winter, any of these could cascade into civilizational catastrophe. We like to believe our intelligence exempts us from natural selection's harsh judgments. But intelligence without preparation merely means we'll understand exactly why we're going extinct. The dinosaurs survived over 160 million years without intelligence. We've existed as a species for 300,000 years, and as a technological civilization for perhaps 2 centuries. We are evolutionarily young, unproven, and arguably more vulnerable than we realize. Yet there is something profound and humbling we must acknowledge. Our existence is a direct consequence of the dinosaurs' extinction. If the asteroid had missed Earth 66 million years ago, if the dinosaurs had survived, mammals would likely still be small nocturnal creatures hiding from predators. There would be no primates, no apes, no humans. Every person alive today exists because a mountain of rock happened to hit the right spot on Earth at exactly the right time to kill the dinosaurs while sparing our mammalian ancestors. We are literally children of catastrophe, born from extinction, products of the void left when giants fell. This should inspire simultaneous humility and gratitude. We did nothing to earn our existence. We inherited it from cosmic chance and our ancestors' accidental possession of survival traits. The dinosaurs were not failures. They were successful beyond measure, and their success meant nothing when conditions changed catastrophically. We are successful now, but our success similarly means nothing if we fail to protect ourselves from threats both predictable and random. The history of life on Earth includes 5 major mass extinctions before the one that killed the dinosaurs, and we are currently causing what many scientists call the 6th mass extinction through habitat destruction, climate change, and overexploitation of species. The difference between current extinctions and previous ones is that we can choose to stop. The asteroid impact was random, unavoidable for the dinosaurs, an act of cosmic violence they could neither prevent nor survive. The current extinction event is not random. It is caused by human choices: deforestation, pollution, greenhouse gas emissions, poaching, habitat fragmentation. Every one of these causes can be addressed by changing how we live, what we prioritize, what we value. The dinosaurs had no choice in their fate. We do. This makes the current extinction simultaneously more tragic and more hopeful than the KPG event. Tragic because these extinctions are preventable and yet continue. Hopeful because prevention is possible if we choose it, if we prioritize long-term survival over short-term convenience, if we recognize that protecting biodiversity protects the ecosystems we depend on. The dinosaur extinction teaches us that life persists, but species do not, that ecosystems recover, but the dead do not return, that success under current conditions predicts nothing about survival when conditions change. These lessons should inform everything from conservation policy to climate action to disaster preparedness to space exploration. We should protect endangered species because extinction is forever, and we cannot predict which species possess traits useful in future catastrophes. We should address climate change because rapid environmental shifts killed the dinosaurs and will kill whatever cannot adapt quickly enough. We should prepare for disasters, including asteroid impacts, pandemics, and nuclear events because our ancestors survived the KPG extinction partly through luck, and we should not rely entirely on luck for our own survival. And we should pursue space exploration and potentially space colonization because single-planet civilizations are vulnerable to planet-scale catastrophes, and spreading beyond Earth provides insurance against terrestrial disasters. The fossil record preserved in rock layers around the world tells a story that repeats with variations. Dominance is temporary, extinction is common, and adaptability matters more than strength. The dinosaurs were extraordinary creatures that dominated their world for longer than any mammal group has dominated since. They evolved incredible diversity and occupied nearly every terrestrial niche. They survived multiple extinction events and climate changes, and they died anyway, not through failure, but through catastrophe beyond their capacity to endure. We should remember them not as cautionary tales of failure, but as testament to both evolution's creativity and nature's indifference. They were successful, and success saved them nothing when an asteroid struck. We are successful now, and our success will save us nothing if we fail to use our intelligence to protect ourselves from similar fates. 66 million years have passed since that terrible morning when the sun rose over a world belonging to dinosaurs. The dust has settled, the climate has stabilized, the ecosystems have rebuilt, filled with different players but functioning according to the same basic principles. Birds, the surviving dinosaurs, number over 10,000 species and inhabit every continent. Their existence proves that dinosaurs did not completely fail, that one lineage navigated the catastrophe successfully and inherited a transformed world. The mammals that survived have diversified into whales and bats, elephants and primates, filling every niche from ocean depths to mountain peaks. And one lineage, our own, has developed technology that allows us to read the story of that ancient catastrophe in rocks and fossils, to calculate the size and speed of the asteroid, to understand the cascade of effects that killed the dinosaurs and spared our ancestors. We have learned what they could never know, that we exist because they died, that their extinction was our beginning, that the last terrible day of the Cretaceous was the first day of the age that produced us. We stand on their graves, and we should stand there with humility, with gratitude, and with determination not to repeat their fate. The dinosaurs could not save themselves. We can. The question is whether we will.